Welcome. Today we're discussing the channel modeling and testing rate versus range in a real fading channel with the model specified by the IEEE. And today our speakers are Steve Shearer, our chief scientist, and Prachi Samkuwar, our systems engineer. Both are based in California. Steve has recently joined us, and prior to octoScope, he's been with the Wi-Fi Alliance. But he has a long career with wireless, including Philips, where he did some R&D on some cellular technology. And then he's been most active in the Wi-Fi Alliance on the coexistence testing with LTE and Wi-Fi, on Wi-Fi 6 certification, and Easy Mesh certification. So Steve's the real expert on the topic here that we're going to cover. And Prachi is our systems engineer in the Bay Area in San Jose, also with Steve there. She's been helping our customers operate the Octobox test beds. She's also our resident expert on the Wi-Fi Alliance testbed that we have fully automated for certification. And prior to octoScope, she's worked at Intel and holds a master's degree. So with that, I'm going to let Steve get us started here.
Thanks, Fanny. So we've had a lot of questions from folks about radio propagation channels, and so we thought we'd do a tutorial and take a bit of a deep dive into some of the aspects of real-world propagation. So these kind of fall into two broad categories. The first is line of sight, where the receiver has basically a direct view of the transmitter. And the second is non-line of sight, where the path is blocked by a wall or reflected off an obstacle. So you can see in the diagram here, there's the large gray box at the top is acting as a reflector. The transmitter path reflects off that and impinges on the receiver. So that is a non-line of sight. The other interesting path is from the transmitter through a wall to the receiver, and as this diagram depicts, there's some considerable attenuation going through that wall. So passing through obstacles significantly attenuates the signal. Reflecting off obstacles delays the arrival time at the receiver, and it also introduces attenuation. So real-world channels have combinations of line of sight, several non-line of sight paths, and these introduce a number of complexities in terms of what the receiver can discern. So typically, delayed paths will cause a more complicated frequency response of the channel. It'll introduce nulls and peaks, as well as attenuation. Whereas typically a line of sight propagation just has a flat frequency response. It's a very simple channel, very useful for a lot of testing. But as we go into more sophisticated Wi-Fi, it becomes more and more important to test the capability of a device in a real-world channel. So this is an image showing in frequency and time the different aspects that happen in these non-line of sight channels. If you take a look across in frequency, you can see nulls that creep in there depending on what frequency, depending on the frequency. But you can see also there's a variation over time as well. So this is a pretty complex thing for a receiver to deal with, and it's important to test their resilience to these complexities. So with that in mind, today we'll study some of these aspects and we'll learn how to successfully test with them. So I'm going to start off with what we call a power delay profile. So a power delay profile depicts the relationship of attenuation and delay for each path. On the left-hand side, you'll see the transmitter who, in the blue there, he's transmitting at time t equals 0. If you look on the far right-hand side, you'll see a green path directly from the transmitter to the receiver. That is the line of sight path, and it arrives almost at t equals 0 at the receiver. Conversely, looking at, for instance, the red path, this bounces off a building and arrives a little bit later at the receiver. So you will see the impulse at T1 there. That's the delayed path off of the buildings. You'll notice it's also attenuated, and that's partly because of the reflection that it underwent, but also because it's a longer distance for it to travel. Same sort of idea with the yellow one. It's bouncing off a building a little bit further away, arrives a little bit later than the red one, and it's also attenuated by a bit more too. Likewise for the purple. So this power delay profile is a very convenient way to describe in a very concise picture what a channel looks like, at least in the time domain. So important to note that it's the physical environment that determines this PDP. There are many different channel models that people use to suit the environment that they're interested in. For instance, if we were to look at a PDP for the Swiss Alps, you'd find that the delays would be considerably further apart because they're reflecting off very distant objects and they arrive significantly later. If you were to look at an urban model, you'd find these delays somewhat shorter. And we're, of course, interested in the indoor model. So we'll take a look at that. I'm going to pause at this point if anybody has any questions or clarifications. Okay, good.
Feel free to post your questions or raise your hand, and we can have a discussion.
All right, so we're going to focus on an indoor model because that's typically where Wi-Fi lives, and we see in an indoor model very often a slightly more complex PDP. You'll see that in this particular PDP, which is the 802.11 model D, there are actually 3 clusters of these impulses. Now, where do these impulses come from? Best thing to try and get a handle on this is to imagine a cluster of energy that bounces back and forth off the walls. So each time it bounces, it's a little lower in amplitude, it's a little later in time, and this kind of continues. If you look, for instance, at the red cluster there, that's what's happening there. It's bouncing back and forth, becoming attenuated each time. General rule of thumb, 10 nanoseconds is 10 feet. If you look at the delays between successive red impulses, it's about 10 nanoseconds. And that would give you an indication that the reflectors are in the order of somewhat like 10 feet apart. But there's a second cluster, and this second cluster marked in yellow, you'll see they are spaced significantly further apart than the red cluster. And these are from slightly more distant objects. Again, bouncing back and forth, and gradually decaying. So the Model D, the .11 Model D actually has a third cluster that they feel is important. And again, that's actually spaced in time a little bit more even than the yellow. So same basically physical analogy. So yeah, so this is a good depiction of an indoor model. These repeated delays have an impact on the frequency response of the channel, as we saw in the picture earlier. They cause nulls and peaks in the frequency response of the channel, and we'll see a bit more of that later on. Right, so as I mentioned...
I'm sorry, Steve, we have a hand raised for the last slide. So Z Huang, I'm going to unmute you here. If you have your question, go ahead.
So you're very quick when you say that's the rule of thumb, 10 nanosecond, 10 feet. Is the 10 feet between the two wall, or is one way or two way? My point is, it's just a...
Well, I was just thinking, speed of light is approximately 1 nanosecond per foot.
Okay.
So that'll be total path length, right?
Oh, total path, then like a bounce, wherever return. Okay, fine.
Yeah. Okay, thank you. Good question. So as we mentioned, there are a number of different models to suit different physical environments. There's been a lot of study done in IEEE, a very good paper produced by, I think, as many as 30 experts in the field. And they came up with a list of typical channel models that are representative of various environments in which Wi-Fi would be used. Very interesting paper. I'd be happy to share the reference with you if you're interested. Drop me an email and I'll get that to you. As you can see, they've got a number of these here. We looked at Model D a little earlier, and that is a typical, it's called typical office. It has certain characteristics. It has, for instance, 3 clusters and so on. A large outdoor space is representative of, much larger distances, much more delay, and probably more clusters as well. Now we're focusing on the residential model because that's very representative of a lot of consumer deployments. Actually, our multipath emulator emulates 2 of the IEEE models defined in that paper. The first is Model A, which, as we mentioned, is a direct line of sight, flat frequency response, no delays, no spectral nulls. But we also implement Model B, which is the residential non-line of sight has 2 clusters, has a delay profile, and introduces frequency nulls and so on in the frequency response of the channel. So these are pretty good models, quite representative of a typical environment for Wi-Fi. I'm going to pause if there are any questions at this point.
We have, let's see, Devin's asking, is Model A equivalent to an anechoic chamber? Am I pronouncing that right?
Yes, it is. Yeah, it's a direct line of sight. Just think of it, transmitter to receiver. They can literally see one another. There's no reflections of anything at all. So it's the simplest channel model that you can get, basically, but it's very useful for a lot of testing too. So, okay, thanks for that question. I'm going to move on. We built the MPE to implement Model B for non-line of sight. And we wanted to compare its time domain impulse response and line that up with the power delay profile that was specified by IEEE. So it's pretty difficult to measure, you know, nanosecond spacing and stuff. But one of the easy ways of doing that is to take the frequency response and do a Fourier transform and transform it into the time domain. So that's exactly what you see here, is the time domain response. And you'll see the 2 clusters from the specification depicted by green and the red markers. And then you'll see the lineup of the actual impulse response of the MPE drawn on the chart as well. So they actually line up pretty closely. So this kind of proves that this is a good representation of the IEEE Model B. Okay, so now we've looked at the time domain response of a real channel. We've compared it against the IEEE specification. And let's zoom out a little bit and take a look at what the MPE is. So the MPE, the multipath emulator, will work from pretty much DC to up in the 8 gigahertz region. It accurately models that IEEE Model B, and it has a bypass switch in it, which allows you to implement Model A as well. So Model A is line of sight, as we discussed, and the switches in the diagram down below show it in line of sight mode. So it's going straight through. We have a programmable attenuator, so we can do rate versus range testing. And when we want to introduce non-line of sight conditions, Model B, we just move those 2 bypass switches and enable the multipath component. So it's a bidirectional 4x4 MIMO link. The interesting aspect of this multipath emulator is that the forward and the reverse path response is identical. So that's very important actually for Wi-Fi, especially when they do channel sounding. It would be very confusing for the devices if they did channel sounding in one direction, but then got a completely different channel response in the other direction. So you'll notice the picture of the device at the top there. You'll see 8 SMA connectors, that shows that it implements four independent channel models. And you notice we don't mark those as either input or output because they serve as both. It's actually a passive implementation, and that is actually one of the unique features that has many advantages. So part of that is that it gives you complete symmetry in the channel, as we mentioned before. But the other part of that is that you can run with very high dynamic range, and you don't end up getting mixing products or noise or spurs and these kinds of things that one sometimes sees in other faders. It's also very wide bandwidth, so you can use a number of channels simultaneously. So for instance, you could imagine that this cluster of devices here could be interspersed across a number of different channels in even the 2.4 and the 5 gigahertz band. You would be able to put them all through the multipath emulator at the same time, and operate the system in that way. As I mentioned, it's a passive implementation, so we don't have to demodulate and then perform DSP functions and then remodulate and so on. The problem with that approach is that dynamic range is an issue, delay is an issue, and with our system we can do the full dynamic range of that wireless link, literally from saturation to disconnection. Just going to pause for any questions if there are.
So Steve, yeah, so John is asking, is the MPE the same thing as a Butler matrix?
Good question. No, it is not. A Butler matrix, creates an orthogonal representation of a linear combination of all its inputs. A multipath emulator introduces a time delay response. Specifically, these time delays associated with a power delay profile. So the the delay through a Butler matrix will probably look more like just one impulse. Whereas in a multipath, meaning there are multiple different time delays as you go through it, it will have multiple impulses showing the delayed copies of the signal.
I think also when we get to the response, we'll see the multipath in frequency. So we should just keep going. There's another question, Steve, about the propagation delay for line of sight. And so that's pretty much in nanoseconds because it's a passive system. There's nothing active. There's no demodulator, remodulator. There's no sampling. It's just RF. So it's probably picoseconds, or even it's just instantaneous propagation delay. So it behaves very much like a house, like you ping and you get some multipath response ringing, bouncing back and forth from the walls. It's very, very realistic model. And the path loss from the MPE, it's mostly due to the actual nulls that cut out the power, and you will see. And it depends on the frequency. Steve has some details on it. So if you hang on, Matt will cover that path loss question that you have.
There's also one more question. What is the range of attenuation? Can MPE expand to support Model C?
It cannot. It only does model B because it has two clusters modeled. But attenuation, it goes, we have the attenuator range of 60 dB inside, but the multipath itself, when it switches in, it introduces anywhere between 10 and 20 dB. It's frequency dependent, additional. So you have between the two line of sight and non-line of sight over 80 dB of range.
Yeah, yeah. So Model C has a very different power delay profile, and that power delay profile is designed to emulate a small office. You'll see if you take a quick look at the chart here, you can see that from the numbers. Okay, so want to look now at the frequency response of the MPE. Here we're looking at it in Model A, line of sight operation. As we mentioned, it does contain a quad attenuator so that you can do rate versus range. Line of sight operation is the red path that we've outlined here with the bypass switch in that position. And this is the frequency response in this configuration. So pretty much DC to well above 7.5 gigahertz up into the 8 gigs. There's very little, or there is some droop across the frequency range, but it is a huge, huge frequency range. If you take a look, if you were to zoom in, for instance, take the 2.4 gigahertz channel, you'll see it's pretty much flat across the 60 megahertz or so that the 2.4 gig ISM band offers. And again, if you were to look at it just zoomed in around 5 gigahertz, you would find it's, to all intents and purposes, completely flat within even quite a wide bandwidth at 5 gigahertz. So this is really this is just a huge frequency span, but it gives you some idea of the flatness. We're going to move now and zoom in to and look at what happens when we go to non-line of sight operation. Remembering that in non-line of sight we have these delayed copies that arrive at the receiver, spaced by those impulses in the power delay profile, and they cause frequency dependent changes, so nulls and peaks. And this picture here gives you an illustration of that channel. So we've now moved these switches to incorporate the multipath. We still have the attenuator, so we can do rate versus range, but we're now implementing IEEE Model B, and just take a look at the frequency response. It's pretty complex. There are lots of spectral nulls, attenuations and stuff going on. There's even the attenuation which you would expect as you increase frequency in the real world as well. So again, this is the full bandwidth, DC to well over 7 gigs. And we're going to zoom into this a little bit more and take a look at what this looks like if we were to zoom into the ISM band. So at this point, I'm just going to pause and see if there are any questions.
So we do have one. Is the time variant or not?
It is not time variant. It is a fixed model. It is equivalent of an empty house where nobody moves. Basically, there are no moving reflectors. It's basically everybody stands still. But you can have time variance in the system For example, a lot of our customers place a device on a turntable. And as the turntable rotates, you do get some Doppler and some frequency shifts with the test antennas. And this is something we'll cover in our next session next week. We have some other questions. Why are the nodes deeper in 6 gigahertz? That's the model. It's the exact model, and that's how it looks.
Yeah.
If you were to build a house to this model, that's what you would get when you do a ping. It'll ring like that.
Part of it, I think, to be honest, is the measurement capabilities of the test instrument. So we're looking over a huge frequency range here, and sometimes these nulls are so narrow that they kind of get lost in the quantization of the measurement instrument. If you zoom into these things, you probably get a better picture.
Okay, you've got another question here from Lincoln. For the plot that showed the 3D channel with frequency, amplitude, and time, most channel models would not varying in time unless the receiver and transmitter are moving, correct? Or the reflectors could move too. And that.
Or the reflectors could move.
Yeah.
Indeed.
And so,
absolutely.
Yeah. So when we rotate on a turntable, we can control that also. Then there's another question. Is the channel model symmetrical for the subcarriers within the OFDMA bandwidth? You want to take a crack at that one, Steve?
Is the channel model symmetrical? The channel model, in terms of delay profile, is symmetrical. Therefore, in terms of frequency, it is symmetrical in terms of uplink and downlink, yes. Perhaps we'll move to the next slide, and that may help answer the OFDMA question.
Okay, there's another question. What instrument does it work with? Will you talk about it later? Yeah, it works with, you can put real devices, off-the-shelf devices across it, or you can use our PAL instruments. And we can cover that in the demo as well. We'll show a live demo of it.
Yeah, so that's a very good question, actually. So this is a model of the channel, and it is valid for Wi-Fi signals. It's valid for Bluetooth signals. It's valid for smart grid signals. Anything that would use in a residential type environment, this path model is exactly valid. It's a representation of a physical model. And it's not tied to any type of device. It's kind of nature doing its work, right?
Yeah, exactly. There's another question, Steve, is from Jim Hackett. Is the MPE frequency response shown here the same for all spatial streams? Okay, so spatial streams, it's the same. It's basically a frequency response, but the spatial streams come into play when we have antennas in the chamber. And that's where you can have multiple streams originating from different angles of arrival. And it's a function of how we hang the antenna. So that's another part of the model. And the answer is you can have spatial streams. We have now, we can do 8 spatial streams with 8 antennas that we keep them at low correlation if we have to control that. But that's the over-the-air part of the test bed.
Yeah. So that's a good point. The channel model itself, the MPE, is identical. But as soon as you hook an antenna and you start talking about different angles of arrival, if you convolve that with the response of the MPE, you will hopefully get different frequency responses for your different antenna placements. Okay, I'm going to move on. We're going to zoom in now into what this complicated response looks like in the 2.4 gig band. So here I'm showing just the 2.4 gig band. We've zoomed in here, and you can see these. You can see the spectral null here. I'm going to move on to take a zoom in at the 5 gigahertz band, which is perhaps a bit more interesting. And here I've looked at 4 20 megahertz bands, 36 through 48. So it's much wider bandwidth than we looked at in 2.4 gig. And you can see there's actually an extra spectral null that is crept in there. So this is pretty representative of a typical channel response that you would get in a house as well. It's part of the reason why you get so-called dead spots in some places in the house. You may find that if you change the channel for that same place in the house, you actually get a very much better reception. So these are all complexities that are not just immediately apparent unless unless you actually start doing some of this testing. Okay. So we've discussed line of sight. We've discussed non-line of sight. We've discussed the fact that as you move out of line of sight into non-line of sight, typically, you've moved into another room. You're now going through a wall, and so you would expect, a dip in attenuation and the introduction of some of the multipath as well. The question is, how do we do this in an automated setup, in an orderly and a controlled way? And so I'm going to pass you on to Prachi, who is going to explain how this is done, and look at some of the results, and then she's going to give us a demo. So Prachi, if you would like to take it away.
Yeah, Steve. Okay, thank you. So the slide you see on the screen right now shows you our MPE line of sight, non-line of sight control. So the image you see on the right, this is how we add MPE on our software UI. So the training interval and the step duration you see, the step duration means after how many seconds you want the attenuation to ramp up. You can specify the start and stop attenuation values, and you can also specify in what steps. So you can specify 5 dB or 10 dB according to what you need to test. There is a line of sight and non-line of sight threshold value which you can enter. So whatever value you enter here, so suppose you enter 10 dB, so that will be the threshold. So at 10 dB, there will be a transition from line of sight to non-line of sight mode. And our MPE has a switchover. So in line of sight, it behaves as a normal attenuator. And when it crosses the threshold, it switches over to the multipath. So you can go to the next slide, Steve. Okay. So this is the picture you see on the right is what I'm going to demo very shortly. So what we are doing in the test is we are setting the threshold, the transition threshold to 10 dB, and we are stepping up the attenuator in 5 dB steps. So you will see that in the diagram, when the MPE is in the line of sight mode, so it behaves as a normal attenuator. So the highlighted portion is in red in the top block diagram, and as soon as it transitions and it crosses the 10 dB mark, it switches over to the multipath. So I'm just gonna dive into the demo for you guys. Steve, if I can have control.
So Prachi, Prachi, there was a question that may have gone with the previous slide, but they're asking, what's the minimum step to configure?
So I guess I have used a minimum step of 3. So you can use 3, 5, whatever.
The minimum step is half a dB.
Half a dB.
You can go in half dB steps.
Okay. Okay. Thanks, Fanny.
Sure.
Right.
Yes, you have the RSSI. So let's see the demo. Or the question is, do we have feedback for the actual attenuation of NLOS for MPE? Yes. You'll see a step in the RSSI.
All right. So let's. Okay. Can you guys see my screen?
Yes.
Yes.
Okay. So okay. On the left side here, you can see that there is our instrument panel. So I'm running a downlink traffic to my StayPal. And this window here under Autotest Attenuators is where I have included, I have added 2 MPEs to give it a full 8x8 signal space. So this here, I'm just specifying the values. So I'm just gonna start the test and show you guys. Okay. Okay, so we are running Wi-Fi 6. So we can see that we are getting an MCS of 11 here. And on the left, if you see, we have a sliding scale. So right now, the attenuation is 10 dB. So the threshold is set to 10 dB. And once it switches, once it crosses the threshold, now it's on 15 dB. So you can see here the RSSI. It went from -50 to -70. So that means you have just crossed the wall, and you can see the drop in the throughput, right? And like in the UI, you can see that we were running at MCS 11. Initially, when we were in line of sight mode, we were getting a data rate of 2400. Our StayPal is a 2-stream device, and we are operating at 160 megahertz. So yeah, you can see the drop in the RSSI as soon as we transition from line of sight to non-line of sight. And yeah, so this is a StackMax. So this is available online, so you guys can like access it and then have a look at this test.
So Prachi, there's a question: who reports the RSSI? Your power sensor. We're running. Prachi is running. We have some slides with the test configuration, but she's using one of our instruments we call a PAL. And this is running between the StayPal, it's a PAL based on the station chipset that we have, and an ASUS AP, correct?
Yes,
Through 8, actually 2 MPs, we have 8 paths through them. Mm-hmm. So we will show you the setup. And the PAL is reporting their RSSI.
Okay. Are there any other questions? Okay. So I guess, Steve, you can just go ahead and start sharing a screen.
Okay. Will you give me?
Yeah, sure.
Oh, yes.
One second. Yeah.
Yeah. All right. Very good. Thank you.
Mm-hmm.
Let me. Okay. So, yeah. So I think it's a good part in the session to open it up for questions and answers. If anybody has.
Did you want to show the test setup too?
Yeah, certainly we can. So this is what we call StackMax.
I don't think we're seeing your slides, Steve.
Oh.
Okay, so measuring throughput. A question is, what tool are we using to measure throughput? So we use our own tool we call multiperf. Multiperf it's a managed endpoint that can do multi-point to multi-point under it. It does run inside iPerf 3, and we're soon adding iPerf 2 as well. And multiperf has capability to report a lot of statistics and information as well.
Are you able to see my screen now?
Yes, we can.
Yes,
and then there's another question. Can you guys please share multipath loss for different IEEE profiles? For profiles, meaning models, I don't think we have it handy, but we can follow up with you, Farron, maybe afterwards. Okay, I think we're done with questions. Sorry.
Okay. This is our stack max, which is set up to run a wide variety of test cases. We make use of these high gain antennas to couple to the device. You see the top duct chamber open there. You'll see the directional antennas. It's got an AP on the turntable, and that allows us to measure rate versus range as we rotate the AP. I want to draw your attention to the box on the lower section, if you can see my cursor. This is the PAL box. This is a rather unique box insofar as it has 16 individual stay pals. So they are they're either Linux or Windows based, but they're 16 individual stay pals, and they can be used as sniffers or as stations, or as combinations of those. So that's something that you may want to look at a little bit more. This is more of a diagrammatic view. You can see the test that we've been running. We have had an ASUS access point in the smart box up top here. We've been using a stay PAL in the PAL box, and here are the two MPEs. Any questions or comments on that so far?
So are you testing the AP as a DUT?
We can test an AP or a station. We
Yeah.
have, in this particular test bed is optimized for AP device under test, but we have other topologies that are more suited for station.
Yeah. I mean, by all means, could put an access point up here. You can put a station under test in this box over here. That would, you know, that gives you the versatility. In this configuration, actually, these three boxes down the center can be configured as a 3-node mesh network, and then you can have a stay under test on the left-hand side here, and you can cause that to roam between the three APs. So that's fairly versatile. This is what we call.
Yeah. Sorry, Steve. Go ahead.
I was just going to say that the box on the left that we call a smart box stay. It has 4 stay pals in it, and those are useful to run as sniffers. Especially useful to run as sniffers, actually. So we have 4 sniffer probes. You can put a probe in each of the boxes, and then we can combine the output of each of those sniffer probes into one Wireshark screen. Sorry, Fanny.
Yeah, no worries. My bad. It's the timing with the Zoom is hard to control. But yes, so we highlighted in red the part of the test bed we're actually using. And so the goal for these seminars is we're going to go through little by little and exercise each part of this test bed and show you what it's for and what it does. Now, next time, we're going to use the turntable that you see, and we're going to show you a few tests that we do with the turntable. Please go ahead, Steve.
Yeah, I was just going to say, we pretty much at the end of our material for today. thank you for listening. I hope that you found it useful. As Fanny mentioned, we're going to run a series of these things. We get questions about stuff all the time, and it's often useful just to spend a little bit of time and dig into these topics. We're trying to keep this mainly technical, with a view to, to learning a little bit about some aspects of Wi-Fi, some aspects of how to test it, and so on. Wi-Fi 6 is very interesting insofar as legacy Wi-Fi is pretty much an AP and a stay, and you can, it's a relatively simple setup. Wi-Fi 6 was really designed to be deployed in dense environments. Now, if you want to test its performance in dense environments, you have to create dense environments, right? And so there are different ways that we can do that. We'll touch on that topic later on as well. So in the meantime, if you have a topic of particular interest to you, please don't hesitate to shoot me a note. We'll try and put something together. We want to make these things relevant. And if there's a topic or a question, please feel free to contact me. I'm based in California, in the Bay Area, and so yeah, feel free to reach out.
Okay, so there's one more question. Was the demo tested on the red path? Correct. It was. We highlighted in red the path that we used, and we actually used 2 MPs. Each one of them is 4x4. We used 2 of them for an 8x8 path because our PAL6 is actually an 8x8 device, and so we can set up links that are 8x8, 8x2, for example, with the 2x2 station and an 8x8 AP. But we use 8 paths in that test bed. And you can have more paths than streams, right? That's theoretical. And so more paths is usually better. It gives you better environment for MIMO. So we're using 8 paths here for this test.
It looks like we have a couple more questions.
Instead of the attenuation, can we plot a polar plot as per their real RSSI? Yes, you can do RSSI. We actually have throughput versus RSSI. I think it also works as polar plot. Let me find out for sure. But definitely throughput versus RSSI is available on the charts, and perhaps you may even be able to pull it up.
One of the useful things is all of these KPIs we store in a database, and since all our instruments are time synchronized using PTP, you can pull out this data and post-process it very easily. So if you want to construct a diagram that is not shown in our UI, you can pull out a CSV file or a JSON file, and you can very easily extract the information and create whatever plot you have interest in doing. We pretty much do that. I've seen people do that quite a lot. All right then. If there no
there's
further...
another question. Is PAL6, PAL1, etc.? Yeah. So in the PAL box, we have a PAL6, which is based on the Qualcomm chipset for the AP. And we also have 16 stay PALs that we numbered them from 1 to 16 for ease of kind of addressing them. But there's an interesting way that the state pals are, there are 4 groups of 4 state pals drive corner antennas in the device under test box. And so we can do multi-user MIMO with up to 4 of them and also OFDMA at the same time. It's a pretty powerful test bed, and as we go through these tutorials, we'll be showing you more and more capabilities there.
So,
yes, so Steve
Franny,
is showing. Yeah, go ahead, Steve. Sorry.
I'll hand it back to you if you have any concluding remarks.
Yeah, we have a lot of controls. So there's do we have any special control with supporting 6E and state pals? Okay, so we have a question, what's your schedule for 6E and state pals? So we're going to support it when the chipsets come out. For 6E, it's probably end of the year or Q1 of next year for our PAL. And state pals the same. We're using currently Intel AX200 chipset. So as soon as there is a version out there of extended frequency, we'll be updating it. And then do we have special control? We do have control. We have actually a lot of control over PAL 6. It's based on the Hawkeye chipset. We have access to the firmware and all the registers. And we turn the PAL 6 into an instrument. And we'll be showing some of those capabilities. So we can control things like MCS, number of streams. We can emulate virtual stations using PAL 6. On the state PAL, we have a little less control, but we still have a fair amount of control for the driver. Enabling, disabling capabilities like security and TWT and KVR and stuff like that. We get all the statistics from the driver that we plot that you saw. So we do have a varying amount of control over the different PALs. Do you have boxes for other models? We don't have other models. We only have Model B, which is a model of a house, which is completely broadband and completely symmetric. But we don't do a programmable fader. And so if you need other models, that would have to be kind of hardwired. That's how we do it in RF. And we haven't done that. Okay, let's see what else. You've got more questions. Oh, in the future, we don't plan other models. In the future, most of our customers are testing in the house, so that's the model they need. All right, well, thank you all very much. We appreciate your joining. It's great to see so many people online, and we hope you'll join us again soon.